Well, isn't 2020 just one of those years? I discovered this morning as I was going over our lesson that during our discussion of the derivative of the natural log of x, I never talked about logarithmic differentiation, which is a tool that we're going to need as we move forward with some of our work. So I'm going to take time to explain the technique now, and we'll spend some time practicing some exercises where we crank out some derivatives. So that's what this video is about. Let's talk about some logarithmic differentiation. I want to start with something that we've already worked with, which is trying to find the derivative of a function like y equals e to the 7x squared. We've already learned how to do the derivative of e to the u. It's just e to the u times u prime. So if I were looking for dy dx here, I'd get e to the 7x squared, because that's e to the u, but I'd have to multiply by 14x, because that's the u prime. So the derivative of e to the 7x squared is 14x e to the 7x squared. And that's something that we've already covered. Okay, now that I've jogged your memory on the exponential function e to the u, let's talk about a different exponential function and see if we can figure out the derivative for that thing. So now I want to think about y equals 3 to the 7x squared. How would we go about finding the derivative for this function? It's not e to the u, it's 3 to the u. Well, that's where logarithmic differentiation comes in. So here's how this thing works. We're going to write down the equation, 3 to the 7x squared, and we're actually going to do the logarithm, take the logarithm of both sides. We're going to apply natural log of whatever functions there, in this case natural log of y, and then natural log of 3x squared to both sides. And then we're going to use the rules of logarithms from algebra class to transform this into something that we can do the derivative of. So check this out. We happen to know that when you have a power, oh goodness, apparently my writing is not great this morning, along with all the other issues I'm having. There we go. What we've learned with logarithms is if there's a power, you can take that exponent and you can put it out in front of the natural log. And that's what we're going to do with this thing. So I'm going to have, I keep bumping that, 7x squared times the natural log of 3. Okay, so I just used the rules of logarithms to move that exponent down. We haven't done any calculus yet. I also want to remind you that now the natural log of 3 is just a constant multiple along with the 7. Okay, so that is an algebraic step that we apply to this equation before we want to go and find the derivative. Now we're going to actually differentiate implicitly. So we're going to use implicit differentiation, just like we have earlier, just like we do with related rates. We're going to differentiate with respect to x. So we already know that the derivative of the natural log of y is just 1 over y, right? That's our natural log formula. But because we're doing implicit differentiation and this thing's not x, we have to multiply by dy over dx because of the chain rule. On this side, as we do implicit differentiation, the 7 and the natural log of 3 are just constants. So the only thing we really have to focus on is this x squared. The derivative of x squared is 2x, so now I have 7 times 2 times the natural log of 3 times x to the first power. And we can clean this up a little bit. It's 14 natural log of 3, or 14x natural log of 3. And then remember, our job was to try and find dy over dx. So to do that, I have to multiply by y on both sides. That'll cancel this out. On this side, instead of multiplying by the letter y, I'm going to multiply by the function y, which is 3 raised to the 7x squared power. And so this thing, which is written in a couple different colors here, this 14x natural log of 3 times 3 to the 7x squared, that is the derivative of y equals 3 to the 7x squared. And we used a technique called logarithmic differentiation, where we did the natural log on both sides of the equation and then used implicit differentiation to find the derivative. And the key to it was this line right here where we moved that exponent out in front of the natural log. That allowed us to use our rules of derivatives that we've already learned to come up with this derivative right here. Okay, let me run through a few more examples of logarithmic differentiation, and then eventually you'll get to try some on your own. One of the things that mathematicians like about logarithms is they simplify expressions. So logarithms turn powers into products, right? They turn exponents into multiplication. They turn products into addition, sums. And when you do that, you simplify the expression. And one of the things it does is it makes the derivative a little easier to figure out. So this thing right here, if we want to find the derivative of this, right now we'd have to use a combination of the quotient rule and the chain rule. And it would be nasty. What I want to show you is that there's an alternate way to do this using logarithmic differentiation where the derivative gets to be a little simpler. So remember, our technique is to take natural log on both sides of this thing. So we'll have natural log of y on the left, and that will equal the natural log of this big nasty quotient on the right. And then before we do any calculus, what we're going to do is decompose this thing using logarithms so that the expressions are easier to work with. So I'm going to march you through that process one step at a time. It should sound familiar from stuff that you've studied in your algebra class. Okay, so the natural log of y, we're not going to mess with that right now. But the first thing I notice is that I have a quotient here. And remember, natural logs can turn quotients into differences, right? It can turn division into subtraction. So instead of the natural log of this big fraction, I can do the natural log of the numerator, which is the cube root of x cubed minus 2, minus the natural log of the denominator, which is the 3x to the 5th minus 2 to the 4th power. And then the other thing I can do to simplify this further, again, we haven't done calculus yet. We're just applying our rules of logarithms, or properties of logs, is I can move these exponents. So remember, this cube root, that's actually a 1/3 exponent. So I'll write that 1/3 here in front of the natural log, natural log of x cubed minus 2. And the same thing with this 4 here. This 4 is an exponent, so I can move that out in front. And so this is 4 natural log of 3x to the 5th minus 2. So we've used the properties of logarithms to break this thing down into smaller pieces. At this point, there's nothing else that we can do to simplify this. The x cubed minus 3, we can't do anything with that little 3. Don't be tempted to bring that out in front. You can't use logarithms to break up a binomial like that. Same thing with 3x to the 5th minus 2. That's an expression, that's a binomial that we're stuck with. At this point, we can start to do implicit differentiation like we did in the last example. So the derivative of natural log of y is 1 over y times dy dx. That's going to be the same every time we do these problems. And then on the right side, we're going to use the rule for the derivative of natural logs, which is going to be u prime over u. So we have the 1/3, but then the derivative of the natural log of x cubed minus 2 is going to be 3x squared over the u, which is x cubed minus 2. And then moving along here, we have the 4 times, again, we're going to do u prime over u, so that is 15x to the 4th over 3x to the 5th minus 2. Now I'm running out of space here, so I'm going to start a clean slide to wrap this problem up. So let's get to a clean slide and we'll simplify some things and write out the derivative. So we're just wrapping up this derivative here. A couple things. Notice the 1/3 times the 3x squared there, we can cancel the 3's. And then I can take the 4 and multiply it by the 15 to get 60. The derivative then will be that expression times the y. So this is going to be x squared over x cubed minus 2 minus 60x to the 4th over 3x to the 5th minus 2. And then I have to multiply both sides by y to get that y to cancel, right? So that'd be like this. I take this and multiply it by y, and this y cancels. And I'm going to take the whole thing over here and multiply by y. But I'm not going to use the letter y. I'm going to use the expression for y, which happens to be the cube root of x cubed minus 2 over 3x to the 5th minus 2 to the 4th power. And so this entire expression now is our derivative. And I'm not expecting you to distribute this and simplify and cancel or anything like that. We want to get the derivative written down. If we need to know the rate of change, we can always plug x in and make the computation. But we've used logarithmic differentiation to get a derivative formula for that crazy function. One other comment on this. If you would have went through and used the quotient rule along with the chain rule, you would get the derivative, but it might not look exactly like this. It'll just be an equivalent expression. Because of the technique we use, logarithmic differentiation, we end up with an expression that has this structure where it's some expression times the original function. So if you go through and do this problem again with the quotient rule, just realize that your answer may not look exactly like this. It'll be an equivalent expression. Okay, how about another example? That last example that I showed you, we could have done that with other rules, right? We said we could have run through the quotient rule along with the chain rule, and we could have arrived at the derivative. But a function like x raised to the x power, we only have one tool available to us, and that is logarithmic differentiation. Because the base of this power is a variable expression, x, and the exponent is also a variable expression, x. So this is much more difficult than e to the x, and it's much more difficult than x squared. Both the base and the exponent have functions of x in them. So we're going to apply logarithmic differentiation to this thing one more time. Not one more time, again in this example. So we're going to have natural log of y. That happens every time, right? And then on the left, we're going to have the natural log of, that's the right, x to the x. And the goal of this is to use the rules of logarithms to make this expression something we can work with. In particular, remember that we can turn this power into a product. So moving forward, we have the natural log of y equals x times the natural log of x. I bring that exponent out in front and make this a product. Now, as we go to attack this thing, we're going to have to use the product rule to find the derivative of this. So it's still a challenge, but it's not as bad as we had up here where there was nothing we could do. So we'll be treating this as u and this as v as we run through our product rule. So let's go ahead and do that implicit differentiation. Remember, the derivative of the natural log of y is 1 over y times the dy over dx due to the chain rule. The product rule for this problem is going to look like this. It's going to be u times v prime, which is 1 over x, plus v, which is the natural log of x, times u prime, which is 1. And this just simplifies to 1 plus natural log of x. And then to solve for dy over dx, we're going to just multiply both sides by y. So I have 1 plus the natural log of x times the original expression, which was x to the x power. Right? All I did after I cleaned this up is I multiplied both sides by y. And I used this version of y. So this thing down here is our derivative of x to the x. It's 1 plus natural log of x, that quantity, times x to the x. And the key to finding this derivative was logarithmic differentiation, which we did here in the first step. Okay, one more example and then we'll get out of this video. So this last one, this is just a more complicated version of the function that we had to work with before. Again, this is a function where the base has a function of x, which has to be sine of x, and then the exponent has a function of x, which is just x. And the only way we can find this derivative is through logarithmic differentiation. So we're going to do the natural log of both sides. This is like a broken record now. That's how the technique works. And then we'll have the natural log of the sine of x raised to the x power. And the whole point of this natural logarithmic differentiation is to get this exponent x out in front. And then we'll have to run through our implicit differentiation. So this is going to be natural log of y equals x times the natural log of sine of x. And when we run through our implicit differentiation, we're still going to have to do the product rule. Remember, this is our u and this is our v. All right, so the derivative of natural log of y is 1 over y times dy over dx. And that's going to equal, okay, so it's going to be u times v prime. So that's going to be x times, and then we have to do u prime over u for this derivative of natural log of sine of x. So that's going to be cosine of x, because the derivative of sine is cosine, over sine of x, because that's our u. So u prime over u. Plus the v, which is natural log of sine of x, times the derivative of x, which is 1. So this is just natural log sine of x. To finish this off, remember, we multiply both sides by y. And I'm going to use this version of y up here. And so my final derivative formula, dy over dx, is, I'm going to write x cotangent x, because the cosine of x over the sine of x can be written as cotangent of x. So x cotangent x plus the natural log of sine of x times sine of x raised to the x power. Which was our original y, right? This is a y right here. And that's this thing. And that is our nasty derivative formula for sine of x raised to the x power. So this technique called logarithmic differentiation, it's useful for finding the derivatives of power functions, exponential functions, 3 to the u, 12 to the u. It's useful in breaking apart complicated quotients so that you can write them out and then use your logarithm derivative formula rather than the quotient rule and the chain rule. And then it's required whenever you have a function of x raised to a function of x, like these last two examples. And so what you'll be practicing in the next exercise is just using this technique to find some derivative formulas. As far as what we're doing, don't worry about simplifying these fancy expressions that we get like this last one here. Write it down with, you're going to have to multiply by y and use the expression for y, but we're not going to distribute and try and cancel stuff. These usually look kind of nasty, and that's okay. They are formulas that we can use if we need to find the rate of change of a function. All right, as usual, you know where to find me if you have questions, and in the meantime, take care.